Welcome to growth and decay. So the idea here is many real world scenarios involve rate of change of a quantity which is directly proportional to the quantity. So we get sort of a basic differential equation. The rate of change Q prime is equal to some constant K times Q. Reworking this, that becomes Q prime minus K times Q is equal to 0. This is our most basic first order linear homogeneous differential equation. We have seen that that has solution Q of t is equal to some constant C e to the kt. So we have seen this with population models. So the most basic population model fit this type. And if we have K is positive, we experience growth. And if K is negative, then we experience decay. The population was on the decline or the population was growing exponentially. So we are going to focus on the real world scenario of radioactive decay. So many chemical elements experience radioactive decay. And in radioactive decay, the nucleus of an atom changes and the element can either change to a different isotope of the same element or it can decay into a completely different element. So, experience radioactive decay where the nucleus changes makeup. And again, the atom can either change to a different isotope of the same element, so in this case, the number of protons stays the same, the number of neutrons changes. Or it can change to a new element or to a different element. In radioactive decay, the quantity of the original isotope and original element rate of change is directly proportional to the quantity, and it's a negative with a negative K. So the rate of change of the original isotope or element is given by Q prime is equal to negative K times Q. So we have a negative constant. And this therefore means that we have Q of T is equal to some constant C e to the negative KT. And then we get something which is called a half-life, which is the amount of time it takes for that quantity to halve, right? So we'll see the half-life. So I'll just say here, the half-life, which is often what we are given, is the time for the quantity to halve. So let's go ahead and take a look at this example of what is called carbon dating, which is our most standard technique of determining how old something is. So it is known that carbon-14 decays exponentially with a half-life of 5,570 years. Archaeologists have recently found a bone with quantity of carbon-14 equal to Q, which is 0.23 times Q naught, where Q naught is the quantity of carbon-14 in the bone if the animal were still living. And we want to know how long ago did the animal die. So in this case, we can assume that Q of T, or Q prime, is equal to negative K times Q, or more officially, we can jump to the formula Q of T is equal to some constant C times e to the negative KT. Now, first up, we're going to use the half-life. So a half-life, and then if we assume Q of 0 is equal to Q naught, then we have Q naught is equal to C e to the 0th. So we get C is Q naught. So we're working with Q of T is equal to Q naught e to the negative KT. Now we're going to use the half-life. So a half-life of 5,570 years, if I remember correctly. Yes. What this means is that it takes 5,570 years for the quantity to reach Q naught divided by 2. So we can then solve for that time, or sorry, we can solve for K. So we have Q of 5,570 is equal to Q naught divided by 2 is equal to Q naught times e to the negative K times 5,570. This means we have 1/2 is equal to e to the negative K times 5,570. Or we can rearrange that, and 2 is equal to e to the positive K times 5,570. This gives us natural log of 2 is equal to K times 5,570, or K is equal to the natural log of 2 divided by 5,570. As a general rule of thumb, If you're given your half-life, that constant is just natural log of 2 divided by the half-life. So we have our formula. Q of t is equal to Q naught times e to the negative natural log of 2 times t divided by, actually, I'm going to rearrange this. It works. All right, times t divided by 5,570. So we are told that the current amount, I apologize for the scrolling, is Q equals 0.23 times Q naught. So the current amount is Q equals 0.23 Q naught. I need to update my screen. So the current amount is Q equals 0.23 Q naught, with T equaling the years since the animal's death. So we are looking at Q of t is equal to 0.23 times Q naught is equal to Q naught times e to the negative natural log of 2 times t divided by 5,570. This means we have 0.23 is equal to e to the negative natural log of 2 times t divided by 5,570, or the natural log of 0.23 is equal to the negative natural log of 2 times t divided by 5,570. And we therefore get that t is equal to negative 5,570 times the natural log of 0.23 divided by the natural log of 2. If we plug this into our calculator, we wind up getting t is equal to 11,810.03 ... So we can say, based off of the amount of carbon 14 in the bone currently, and what we would have assumed to be the amount at time of death. So based off the amount of carbon 14 currently, and the assumed amount at the time of death, we estimate the animal died at 11,810 years ago. So you may have worked with carbon dating in chemistry before. Again, once we have that basic differential equation, it's pretty quick to solve. And so you probably worked with it without the differential equation, just with the general form. But at its root is technically a differential equation.